Hello. In this section, we are talking about a certain series type that is known as an alternating series. So, in the past two sections, we had the integral test and the comparison test. And for both of those, one of the very first things we had to check was, are the terms positive? For the integral test, we needed to check if the related function was positive. And for the comparison test, we needed to check that the sequence had positive terms before we could apply their tests. So, not every series is only positive. Some series have negative terms. And an important type that has both this positive and negative is known as an alternating series. An alternating series is very specific in how it has positive and negative, in that it just switches back and forth every term. So, several examples here. We first have the example of -1/2 to the n minus 1. When I plug in 1, I get -1/2 to the 0, which is 1. When I plug in 2, I get -1/2 to the first, which is -1/2. When I plug in 3, we get -1/2 to the second, which is a positive 1/4 because negative times negative. When we plug in 4, we get -1/2 to the third, which is a -1/8. And then it would be positive 1/16, and so on. Notice the signs switch back and forth. We have a positive, then a negative, then a positive, then a negative, then a positive, and it will keep that pattern. That is what we mean by an alternating series. In the second example of the -1 to the n plus 1 e to the 3n, this -1 to the n plus 1, when n is odd, you add 1 to an odd number, you get an even. -1 to an even is positive. And -1 to an odd number is negative. So this series, if we write out a few terms, -1 squared is 1 times e to the 3 over 1 is e cubed. -1 cubed is negative e to the 3 over 2 plus, because we'd be plugging in 3 next, -1 to the 4th is a positive e to the 3 over 3 is e to the 1st minus e to the 3 over 4, and again, so on. The signs switching each time. Taking a look at this lower right-hand corner next, -1 to the n, 1 over n. When I plug in 1, I get -1 times 1 over 1, or -1. When I plug in 2, I get -1 squared, which is positive, 1 over 2. Then -1/3 plus 1/4 minus 1/5, and so on. This series has a special name as well, which we'll talk about a little bit later, but it is known as the alternating harmonic. It is the harmonic series, series of 1 over n, but that negative 1 to the n is making it switch back and forth. So this is known as the alternating harmonic. And then our last example, if we pay attention to the other three, there was always a negative with some exponent in all three cases. This one, there is not a single negative number written. However, if we look at this sequence cosine of n pi, that sequence, when n is 1, we're looking at cosine of pi, which is negative 1. When n is 2, we have cosine of 2 pi, which is a positive 1. When n is 3, we have cosine of 3 pi, negative 1. Maybe starting to see the pattern. Cosine n pi is the sequence that just switches back and forth between 1 and negative 1. This is the same as writing negative 1 to the n. So this is the same as the series n equals 1 to infinity of negative 1 to the n over n cubed, which will ultimately end up looking like, when we plug in 1, we get negative 1 over 1 cubed. Plus, when we plug in 2, we have 1 over 2 cubed, which is 8, minus 1 over 27, and we continue. Plus 1 over 64, and so on. Now, before formally starting to talk about this alternating series, there's a little bit of a question of what is this difference between negative 1 to the n plus 1 and negative 1 to the n. And what that does, especially if we have the same starting lower bound, is it's changing, do we start with a positive or a negative? If you notice, when we had the negative 1 to the n plus 1, we start with a positive because plugging in our lower bound gives us an even exponent on the negative. Negative to a even is a positive number. So we start with a positive. When our lower bound is n equals 1, and we have negative 1 to the n, we start off with a negative number. So the only difference between this negative 1 to the n plus 1 and negative 1 to the n is how does the sequence of terms start out? Does it start out positive or does it start out negative? So pay attention to that lower bound and the exponent to know, is this a negative, positive, negative, positive, or is it positive, negative, positive, negative? So formally, an alternating series is some series. We're going to have our lower bound be 1, but it could be 0, it could be 5. Lower bound could be anything, but be the series n equals 1 of some sequence, which that sequence can also be rewritten as negative 1 to the n times a in completely positive sequence, or n equals 1 to infinity of negative 1 to the n plus or minus 1. Again, changing whether we start with a positive number or a negative number times that sequence b sub n, where I said b sub n is a positive sequence. So if we have this -1 to the n, or there's a piece that is the same as -1 to an exponent, that is going to be an alternating series. So our alternating series test is given an alternating series as above. So a series that has some sequence b sub n times -1 to the n. We have two properties to check. First, if the limit as n goes to infinity of b sub n equals 0. So look at the limit of the sequence, make sure that is 0. I will say now, this is the divergence test in disguise. We do need to check it. But while we are checking this, in the background, we're checking the divergence test. This isn't quite the divergence test, but it's very close. So we first check that the limit of the sequence b sub n goes to 0. And 2, b sub n plus 1 is less than b sub n. This means the sequence is decreasing for all n greater than or equal to some number n. n equals 1 to infinity of a sub n. Notice the properties are about b sub n, but this will tell us about the alternating series. Tell us about this alternating series. Then the series converges. Unfortunately, the alternating series test cannot tell us or cannot prove divergence, and that's where we need to know this first line is the divergence test in disguise. Because if something's gonna fail, it's probably that first one. Doesn't mean the second one can't. We do still need to check the second. But if something's gonna fail, it's gonna be this divergence test in disguise, and that will tell us, go look at the divergence test. And we'll see that in an example. So we have this test now, and it's just these two properties. The limit goes to 0, and the sequence b sub n is decreasing. Why does this work? Why are those two conditions all we need? Let's consider having these two conditions. So we're on some number line, and we're looking at the series -1 to the n of b sub n from n equals 1 to infinity. We know that we want to look at the sequence of partial sums to determine if a series is converging or diverging. If a series is converging or diverging, we look at the sequence of partial sums. So the first partial sum, and just to have the first term be positive, I adjusted that series to be -1 to the n plus 1. This would still work if our first term is negative, but to have our first term be positive, just made that exponent an n plus 1. The first term of this sequence, when I plug in 1, would be -1 squared, so positive, and it would be the first term of the sequence b sub n, so b sub 1. That is the first partial sum. So on a number line, what that would look like is starting at 0, adding b sub 1, and we'd land someplace at b sub 1. The second partial sum is the first two terms. So the first term is b sub 1, and then the second term, when I plug in 2, I'd have -1 cubed, so negative, of the second term of the sequence. And so taking b sub 1 and subtracting b sub 2, I'm going to go back on my number line. So here is where we land for that first partial sum. Here on the number line is where we land for the second partial sum. Notice I made the second line shorter than the first line. Why? Well, because the sequence is decreasing. So each time I add on another term, the length of that term on this number line is going to be shorter. So if we looked at S3, we're going to take b sub 1 minus b sub 2 and then add on, because 3 into the sequence would be -1 to the 4th b sub 3. Add on b sub 3. This term is smaller than b sub 2, and we're picking up where we left off and going some distance that's shorter. So there is the third partial sum. And so it's going to keep decreasing. And then the question is, like, how do we know it ends up decreasing enough? Why can it not just keep staying in this large back and forth and be such that it's not really getting any closer in? Well, we also know the limit of these lines starts going to 0. So eventually, as we continue down, eventually these lines are going to be very short and go to 0. So that eventually we have, kind of like the telescoping series, we have telescoped in or narrowed down into this one singular sum. So those two properties play together to say we're going to narrow in on a singular sum. So this is why this alternating series test works. In the next video, we're going to take a look at a few examples of actually using this alternating series test.